Welcome to this video on differential calculus optimization. In this video we're going to look at the science of making something the best it can possibly be. Therefore, optimization is the process of finding the best possible solution for a given situation. When working mathematically, this generally indicates the need to determine max or min values of a function and often involves the use of differential calculus. So to do this particular type of mathematics, there's a set amount of steps that you follow to go from start to finish, or unoptimized to optimized. So step 1, where appropriate, create a well-labeled diagram. Secondly, construct a formula for the variable to be optimized as the subject. Part 2b, express the formula as a function in terms of a single variable. In this case, we usually do it as x, but again, it's not mandatory. Alright, and part C, discuss the logical domain if necessary. So think about if we're talking about, say, distance or volume or length or area. When we're talking about a logical domain, consider that we can't get a negative area. We very rarely get a negative distance. Again, it's possible, but it doesn't usually happen. And similarly for volume, we typically don't see negative quantities of those. So think about the domain. Usually we're only going to be looking at when x is above 0 or positive answers. Alright, so step 3. This is when we really get into the optimization process and where differential calculus stands in. So step 3, part A, we differentiate. Part B, equate to 0 and solve. Reason being, we're looking for the stationary points. Right, part C, draw a sine diagram to determine any local minima and maxima. And part D, check the endpoints if necessary. Reason being is that with the endpoints we might see values that are greater or less than the local maxima and minima. So just check all of your values. Right, now step 4, identify the optimal solution and write a sentence. So this part, it's all about communication. So you've done all the math. Now it's time to explain what it is you've actually done. So when we say identify the optimal solution and write the sentence, be sure that you're actually answering the question that was asked at the beginning. So solution and write a sentence, being sure to answer the question. Put a smiley face. Example 1, a loop of string of length 100 centimeters is formed into a rectangle. Find the maximum area that can be formed using this loop of string. Alright, so having a look at what we've got here is that we're trying to find the area of a rectangle. It is the maximum area, and the constraints are that we have to use a loop of string of length 100 centimeters. Alright, so if I draw that, we're going to have a length of string, we'll call it P, equals 100 centimeters, and we're drawing it into some sort of rectangle like that. And being a rectangle, the sides, these two have to be equal and these two have to be equal here. The perimeter is still 100 centimeters. And let's label the sides. We'll call this one over here, this top one, we'll call it x, and this side one, we'll call it y. And therefore, our area is going to be x times y. Alright. Now, in terms of the perimeter for this shape, we're going to get perimeter equals 100 centimeters, of course. And more specifically, if we were going to write it in terms of x and y, and I'll throw the 100 centimeters over there, and it's going to be 2x plus 2y. So all the sides have to sum to equal 100 centimeters. Now rearranging in terms of y, we'll go 2y equals 100 minus 2x, and therefore y is equal to 50 take x. Alright, cool. So actually let's go up and just recap. So draw a well-labeled diagram. Okay, that looks pretty good in my opinion. Then construct a formula of the variable optimized as the subject. So this x and y here, yep. Part B, forming function, single variable, usually x. Discuss the logical domain, haven't done that yet. And then 3, differentiate. Okay, so think about this. When we're talking about the perimeter, it has one constraint. Mostly in a physical world, the perimeter must be positive. Alright, so basically our perimeter must be positive, and therefore our area must be positive. So in which case, what we're looking at here is the values of x and y. What we're going to find is that x has to be 0 is less than x is less than 50. So pretty much x, it can't be 0 or else we won't have a rectangle, and it can't be 50 or else we won't have a rectangle again. It's got to be somewhere between 0 and 50. Alright, now we've got a function that describes the perimeter. Now let's go a function that's going to describe the area. So the area itself is going to be x times y, and we know that x is what we're working with, and we'll describe the area itself in terms of simply just y. So it will be 50 take x, and therefore that will be 50x minus x squared. So this will be our function that describes area. Alright, looking pretty good so far. Okay, so remember, what is it that we're trying to do in this question? And it is, we're trying to find the maximum area that can be used to form the loop. So pretty much, we're going to have a look at this function here, so area. So when are we going to get the maximum value? Now, in the past when you've done applications questions, simply just throw it in your calculator and you get the value. So if you graph this function here, firstly it's an order 2, second order, so it's a parabola. It's got the negative x here, so it's going to be a concave down. And what it is that the, where is it? Put the a there and the x here. So what we're going to find is that the maximum area is at this point here, which happens to be a stationary point. So effectively, this will be the max value of area. Now the question at hand is, well, how do we find that value? So there's a number of ways. In the way we're going to use today, it's simply by using calculus. So remember that this point here, that's a stationary point. Now if we go for calculus as stationary points, if I find the derivative of this function simply by inspecting, this will be positive, negative, stationary point. So therefore the derivative of this function is going to look something like that. So this will be dA over dx, or change in area with respect to change in x, and this is going to occur at x and 0. So actually we'll get rid of x and we'll call it x stationary and 0. So therefore this guy up here, this will be at x stationary and f, right, not quite, and this will be at the max area. Alright, so the question itself is asking us to find this point right here. Now, as I've alluded, what we're going to do is to find this point, we're going to take the derivative of our area function. So we're going to go area equals 50x minus x squared. Therefore, we're going to go dA over dx, which will be simple power rule, 50 minus 2x. And then we're looking for this point here. So we're going to say let x equal 0. Not let x, let dA over dx equal 0. And therefore dA over dx is 0, 50 minus 2x, rearranging for x. X simply equals 25. Now if the stationary point is at 25, to find, let's get rid of this guy, this is at now 25, then what we're going to look for is this guy over here. So to find that point there, we simply sub back in area equals 50x minus x squared, let x equal 25, and this just happens to be 625 if I do that quickly in my head. So the stationary point, the value of y is 625. So looking back up, the question asked us to find the maximum area for a loop of string formed into a rectangle that is length of 100 centimeters. In this case, we find that it equals 625 centimeters squared. And then finishing off, we can say the maximum area formed by a 100 centimeter string arranged into the shape of a rectangle is 625 centimeters squared. Now, one thing we could have done slightly different for this solution is we could have gone for a sine diagram. Now, the reason I opted not to do it was simply because it was already apparent. It's already apparent what was going on based on what we could see in the rough sketch above. So a stationary point being at 25, and we knew that this was going to be positive, this was going to be negative, and therefore we're seeing a stationary point that it's a turning point that goes from positive to negative, like so. So in a question where we didn't know the shape of this particular graph, we would go for a sine diagram like this. Alright, but pretty much we can solve the question simply by inspection like so. Alright, going down for example 2, a simple cylindrical can is to have a volume of 500 centimeters cubed. Find the dimensions of the can which can minimize the area of the sheet metal used in construction. Okay, interesting. So we're going for a cylindrical can with volume of 500 centimeters cubed. So let's see how good my sketching skills are. Cylindrical can, and the volume V equals 500 centimeters cubed. Now the defining characteristics of this sort of shape is that we're going to have a radius. Oops. We're going to have a radius, and we're going to have an height. Now find the dimensions of the can which can minimize the area of the sheet metal used in construction. Alright, so we have to flatten this out. So flattening out this cylindrical object, we're going to get something like that, and that's going to translate into radius. This will be the height, of course, still, and the trickiest one of them all is this area here is going to be the circumference of the circle, because if we wrap all of this up, if we roll all of this around, this side or this edge here refers to the length here. So the surface area for the cylinder is going to be surface area is going to be 2 times pi r squared, because we have one circle here and one circle here, and then we've got this guy in here, so that's going to be plus 2 pi r h, like so. Okay, so that's the first part. Now we need to look at our constraint. We know that the cylinder has to be 500 centimeters cubed. So the volume of a cylinder is going to be pi r squared multiplied by its height, and that's equal to 500. Alright, so let's rewrite that. Perfect. Okay, now let's look at the question again. A simple cylindrical can, so cylindrical is to have a volume of 500 centimeters cubed. Find the dimensions of the can which can minimize the area of the sheet metal used in construction. So find the dimensions of the can that can minimize the area of the sheet metal used. Dimensions. Okay, so we've got two dimensions we can work with. There is the height and there is the radius, of course. So what we need to do is we need to pick which dimension we're going to vary here. What I'm thinking is, because we've got these r squareds in the equation, it might be easier to work with the h's here. And I think this would be really easy to rearrange in terms of h there. So what I'm going to do is I'm going to rearrange the volume in terms of the height. So we're going to find that h is equal to, 500 divided by pi r squared. And therefore the surface area is going to equal 2 pi r squared plus 2 pi r, and then this will be 500, all that divided by pi r squared. So that's going to cancel, that'll cancel, that'll cancel, that'll cancel, and then it's simply 2 pi r squared plus 1000 over r, and rather than writing over r, we will simply do it as r to the negative 1. So what we've got is, we'll call it, I'll abbreviate it to simply A. Surface area can be described as 2 pi r squared plus 100 divided by, sorry, not 100, 1000 divided by r to the negative 1. 1000 times r to the negative 1. Alright, cool. Now the question itself is, find the dimensions of the minimum area. Sorry, find the dimensions to minimize the area. So what we need to do is we need to figure out how, if we graph this, for example, and we had, I know, a graph that looks something like that. It's not going to, but just suppose it did. What we'd be looking for is this location here, or potentially this location over here. So the minimum value that it can assume. Now, consider the domain of this particular function. The radius itself, it can't be a negative number. So what we're going to find is that the domain is going to be such that r is greater than 0. There might be an upper limit of the domain, but we'll just leave it off for now. Yeah, we'll just leave it out for now. Okay, basically what this becomes, because I don't know what this function is going to look like, I can't do the approach I took in the last question where I just sort of did a rough sketch and said, okay, it's going to be here because we can guess what it looks like. This one, it's some sort of weird function. So what we need to do is we need to first find the derivative, and then we're going to go for a sine diagram. So we're going to go dA over dx is, not dx, dr. dA over dr is going to be, that will be 2 times 2 pi r plus -1 times 1000 r to the -2. That will become 4 pi r minus 1000 r to the -2. So dA over dr, change in area with respect to change in radius, is 4 pi r minus 1000 r to the -2. Now remember, we're looking, we've got to look for the local maxima and minima in this case now. So what we're going to say is let dA over dr equal 0. And now it's simply a case of solving for r. Alright, further solving it, we've got this strange equation with an r and a r to the -2. Let's get rid of the r to the -2 by multiplying both sides of the equation through by r squared. So we're going to get 4 pi r cubed minus 1000. Then rearranging in terms of r, we're going to get 4 pi r cubed 1000. And r cubed will equal 1000 divided by 4 pi. Moving down, that will equal, r will be the cube root of 1000 divided by 4 pi, and I can clean that up a little bit more. We'll go pi over, and that's going to be 250, like so. So we're going to expect potentially at least one real solution in this case. This tells us that there's one stationary point at r equals the cube root of 250 over pi. So stationary point. Alright, so we know where the stationary point is. Now we need to figure out, is this stationary point going to be a maximum or is it going to be a minimum? So the way in which we can do this is we can do a sine diagram. So we'll go sine diagram of, we'll call it dA over dr. And the sine diagram is going to look like 1, 2, 3, 4, 5. It's a bit messy. The cube root of 250 over pi. Alright, and what we want to do is we want to deduce if it's going to be concave up or concave down. If it's concave up, then it's a case of this is going to be a minimum. If it's concave down, then what we find is this is going to be a maximum and our minimum will be somewhere on this side or this side. So let's just pray that it's like that. Alright, now the way in which we can do it is we need to test test on this side and test on this side. Now, if we evaluate the cube root of 250 over pi, it's going to be roughly equal to 4.3. So what we're going to do is we'll say test dA over dr for r equals, we'll say something greater, and test for dA over dr something that is, we'll say less than, so 3. And what we're going to find is that if we go for dA over dr when r equals 3, what we find is that it's actually less than, or it's actually in the negative, so it's negative there. And if we go for dA over dr where r equals 5, we're actually in the positive. So what we find is that we're going from negative back up to positive. So this part here, it's concave up. And because it's concave up, that infers that this is the minimum. This is a minima. And therefore, what was the question again? The minimum area, the dimension for R that will give the minimum area is R equals the cube root of 250 over pi. Now, you don't have to leave it in this exact form here, but having said that, you don't have to evaluate it either. Me personally, I choose to leave it in its exact form purely because I don't like having to deal with rounding errors. So this is an example of how we would optimize a problem involving volume and area.